All right, in this video, I'm going to do a deep walkthrough of the tractor beam analog phaser circuit. The tractor beam was originally named the Enterprise circuit and changed its name a few years in. So it's basically the same circuit throughout, but been updated throughout the years. And so this is the last version. This is the SPS version. So I wanted to walk you through that. Okay, here we go. All right, first, here's the input stage. The input stage is actually not just a buffer or a gain stage. It actually reduces the gain. And the reason being is that no matter how much power, external power, charge pump, whatever you throw at this circuit, it's limited by the configuration of the GeoFex that are controlling the phasing. So I have a little circuit here that actually slightly reduces the gain just a little bit to give it, I found just a little bit, gave it some better clean headroom before distortion. It's not a ton. I mean, we're talking like 1 dB maybe, but I found that it made a difference. So I stuck with that. You can certainly adjust if you want it to be unity gain, you just make those the same value. So you could make that 470K or that 390K. But if you're finding you're getting too much distortion, you can reduce that value. And if you're finding you're not getting any distortion at all, but you want to reduce the noise floor, the best way to do that is to lower that value. So you would increase the gain and until, as long as it's still clean. And then you have less noise from later stages because you don't have to crank the volume at the end. All right, so that's that. This right here is a coupling capacitor, just to make sure no stray DC voltages mess up with other pedals. Okay, and so that's the input stage. This little cap there is filtering out some really high frequencies, mostly to keep it so that when we start to send a lot of feedback, if we allow some sort of stray really high frequencies, sometimes it can just be interference from, these are magnetic pickups and coils and stuff. Could even be inaudible stuff that we're filtering out. If we start feeding that back on itself, it can start to self-oscillate and kind of destabilize the circuit. So this is filtering out some of those really super high frequencies. All right, next, here we go. Okay, so this is the main phase section. This is where all the magic happens. And so each one of these little op amps is an all-pass filter. It's called an all-pass filter. Go ahead and look it up. But basically what it is a unity gain or close to unity gain filter that all it does is adjust the phase relationship of different frequencies to each other. So that'd be something actually really to understand how this circuit works. It would be really good to actually look that up, all-pass filter, and kind of do an in-depth exploration. But basically, the configuration here of an all-pass filter typically is a resistor going into the negative, and then a capacitor going into the positive, and then shunted to ground through a resistor, creating that would be creating a high pass filter to the positive. Or you could do the other way. You could actually have a resistor going here, and then this would be a capacitor. The reason why it's configured this way, capacitor then to a resistor, the GeoFex is acting like a resistor. Is because it's easier to get to GeoFex to behave nice in that configuration. That's why it's there. Now, there's some things that are hidden here, and it'd be great if someone wanted to take the time to really make this schematic even more plain. There's a lot of strip resistors that I use to simplify the size of the circuit, so all this crazy amount of stuff can fit. And so all these little pins represent resistors. So I'll just kind of give you sort of the lowdown. There is a 2.2K resistor that is connected to right here, and that goes to the negative input. There's some pins to represent it on the schematic, but it's a 2.2K. It's in a strip resistor form. And then there's a 2.2K resistor that goes from the negative to the output. So you see where this capacitor is connected? In parallel to that is a 2.2K resistor. And then the same thing continues. So from here to that negative is a 2.2K, and then from that negative to that output is a 2.2K. From that output to that negative is a 2.2K. From that negative to that output is 2.2, and so on, all the way down the chain. Okay. And then another strip resistor is in parallel with the JFET. So you can actually see a pin right here, and I don't see the other pin. This strip resistor is one where it has essentially like a single input and then has a bunch of resistors coming out of it in an array. And so the common connection on this resistor is ground. So all these resistors are going to ground, but where they go is connected to this pin, this, what would that be? Shoot, I'm going to mess it up. Drain source. Source? No, drain. Okay, whatever. I'm just in my mind right now, just blanking. But to that connection point on the JFET here, it's in parallel to it. And the reason for that is that if you allow the JFET to just do the resistance change on its own, it can sort of start to exceed a value at which basically phasing won't happen anymore. Or you're kind of creating that maximum, where does it stop? And so you can feel free to experiment with that. I tried to experiment with something that had a really good sort of feel to the range and sweep and such. So, but you can experiment. Again, the one that I'm using is a 10K, and that one's where it has a common and then a bunch of parallel resistors. The one up here, the 2.2K strip, is just, they're just completely separate resistors. So that's how that's configured. Okay. All right, so now what's happening here is that this JFET is that variable resistor, and when it varies the resistance in this configuration in an all-pass filter, you change the phase relationship from high frequencies to low frequencies. Again, search all-pass filter to better understand this. Now here's the key. If this, and this are doing actions out of sequence, out of synchronization with each other, you'll get phasing, but it won't be this strong, like resonant phasing, where you get this strong, like sweep, because it's not, they're not aligned on the same frequency at the same time. And so I hand match what's called the VGS, the voltage gate to source, as far as what's going to turn on or turn off that transistor. Is basically set to a specific resistance. Another good thing to search, and I'll put it in the link below, is a GeoFex, GeoFex article on how to hand match these, and actually specifically this part, it's where I learned. So I'll link that. But also this is a really hard to find part, so it's hard to find, so it's going to be expensive. And if you need to hand match 4 of them, you can't just buy 4. They're not going to match. So you have to buy a bunch and then hand match them. So what I'm going to do is, I've got a huge set that I had acquired a while ago, and I'm going to hand match them, and then I'm going to make them available on the website. It's not available this second, but it will be soon. Okay. So there you go. And then the other thing is that you'll notice that this capacitor value here is 0.22U, and that one's 0.22U. And you'll notice there's another 0.22U and another 0.22U. That capacitor, if it's the same all the way through, then you get that uniformity of sweep. However, if you change the value of the capacitor, one, you can change kind of the range of the sweep and the feel of the sweep. But the other thing that you can do is, if they don't match anymore, now you don't get that strong phase resonance, but you're still getting this phase effect, and actually you're getting a pitch shifting effect still, because you're still causing the signal, now at different points for different frequencies, to go back and forward in time. And so that de-emphasizes the resonance of the phaser, that sort of strong connective frequency, and begins to sort of bring out more sort of that juicy pitch vibrato of the phaser sound. That's still going on in a regular phaser, but it's not as prominent. Okay. So that's what this switch here is for. It's to toggle out the capacitors to make it so that those two stages don't act in the same sort of synchronous way. And the way because it's a on switch, a DPTT on, what happens is that in one position, the top, like, I don't remember if it's top or bottom, one position is phase, and the other position is vibe, which means you go from the 0.22U's phase, matched all the way across, to vibe, meaning the 12N and the 1U. This one got larger, that one got smaller. And feel free to play with those to play with that. But then the middle position only toggles out one of them, and I believe it toggles this one. I'm going to feel free to experiment. I'm pretty certain it's this one, because what my goal is to, this higher value one gives more of a deeper throb in the phase shifting. And so if I take away that, you get this less resonant, because they're not all in like lockstep. It's less resonant, but it's not like this throbby the vibrato type thing. It's more like this smooth. So it's got this smoother character. Okay, so there you go. The only last thing to mention here is that the output right here at the end, it's fed back all the way back, and this potentiometer here is controlling, do I feed it back to the first stage, or do I feed it back to the second stage? And if you're halfway in between, you're feeding evenly, which will basically offset, because this is an inverting amplifier. So if you're feeding it evenly, you're going to send a signal here and the same signal there, but then this is going to invert that signal. It's going to do a little bit of phase shifting to it, but it's going to invert it, and then it's going to combine it with this other signal and essentially offset it, or not perfectly, but practically. So in the middle position, there's much less resonance or feedback. But as you feed back to positive or negative, you'll start to emphasize as those phase shifts start to line up or cancel against each other, because they're destructively canceling. A peak and a valley are matching up, canceling, and that changes which frequency all the time. So you're just going to make those resonant peaks or those troughs more. You're going to exaggerate them, and whether you you send more feedback to the first stage or send more feedback to the second stage will change those frequency relationships, which frequencies are getting boosted, which frequencies are getting cut, and how that happens as the phase sweep goes through. All right, that's a lot, but that's the key to understanding just this whole thing. Everything else around there is just a structure built around this to make the most use out of it. So let's continue. Okay, so this is the mix stage, and in a phaser, if you were to mix, if you were just to have the pure phaser sound, so if you were to dial this way, I think that's a dry, so if I dial it that way, it shorts out, there's a ground, it shorts that out, leaving just the phaser side. You wouldn't get as much sort of phase sweep, that sort of airy phase sweep sound, because that comes from the slight phase shifting being matched up with something that isn't phase shifting and having those constructive and destructive like interactions of the different frequencies. If you just have the phaser here, yeah, you can get that through the feedback knob, getting some of that resonance, but you're going to emphasize more the phasers shifting it backwards and forward in time. In order to do that, to go forward in time, you mean say, let's see, we're going forward in time, backwards in time. I'm trying to remember. One of them's going to stretch the wave, one of them's going to compress it, stretch it, make it lower frequency, compress it, make it higher. So you're going to hear more pitch shift. So if you crank this all to the phaser side, you're going to get more of a vibrato sound. And if you go more towards the dry side, obviously the effect will start to minimize and get less and less and less. And what I also notice is that the thing you hear, the thing that gets taken away quicker, if there's two parts of a phaser, there's the pitch change, the pitch vibrato essentially, and then that phase resonance. I find that the pitch modulation is the thing that starts to disappear to your ear faster, and the thing that disappears last is that sort of airy phase thing. So as you get there, there's less pitch, but you start to hear, you still hear, it's not that sort of airy phaseness. So what ends up happening is that the strongest position for the maximum phaser like juiciness effects is actually at noon, a perfect blend of the two, because you get both of those, lots of that pitch modulation coming through, but also a lot of that constructive destructive relationship. Okay, next part. This right down here is the LFO. It essentially is controlling the speed and the depth of the voltage that's hitting those JFETs to set their resistance, and their resistance is what sets the whole phase shift in motion. So here is the LFO. I'm not going to go into this exact type. In fact, this is one of the things, like LFOs, still parts of them are a little bit of a mystery to me. I'm not an electrical engineer, so there's certain parts I haven't studied as much. However, I can tell you that thing is going to affect the range of the LFO. Like, you increase that value, it gets slower. Shrink it, it gets faster. But also, this is the speed knob, so the more resistance here, the slower you're going to get as well. And so this resistor ends up setting the maximum speed, and then whatever this is, when you crank it and in this case crank it down for maximum resistance, that would set the slowest speed, and that's in conjunction with this capacitor right there. Okay. All right, and then from there, this LFO is sent out here, and then this is just a simple like volume knob essentially. This is signal in, and you have a potentiometer going to ground, and then this just, do I go up towards the signal or down towards ground? That adjusts the strength of that signal. So this is the width knob, so you can go to completely off, no LFO, up to maximum there, and that's just sent to a buffer to make sure it's acting properly. And then this whole circuit is part of the phase 90 circuit. I've adjusted it a little bit for use with a charge pump that's positive and negative voltage supply. But it's basically what it's doing is it's setting the center voltage, letting you tune the center voltage at which you hit the, at which it swings, the voltage swings to hit those JFETs. And you've got to tune that to that specific set. And it's pretty particular, meaning just a small change will change the sound, and sometimes even completely remove the phase shifting, because you're going like this, but you're in like some inaudible territory or some territory where it's just not, you're not hearing the pitch shifting and all that kind of stuff. So that's what this trim pot is for. It's taking this voltage from a Zener diode and then essentially letting you select a voltage within a more narrow range, which lets you dial it in better. If this thing went from positive down to negative, it'd be so hard to dial in. So this narrows it down to kind of where that ideal range is it's gonna be somewhere in there. And then it goes to here, and then this control, what I have found is that if you dial this in just right, this control can, more resistance will result in, and now I'm trying to think, more resistance will result in sweeping that frequency of the shift up, and less resistance will result in that frequency that the signal bounces around, the phase shifting bounces around down. And so that's this is the center knob, kind of shifting the center frequency relationship. Okay, that's a lot. I will also note that this resistor is really high value for a reason. It's combined with this capacitor here to create a low-pass filter to smooth out. If you take away that capacitor, you're going to have some real jumps. It's not going to be this smooth pacing action, especially at lower frequencies of the LFO, slower speeds. Okay, but you can certainly play with that relationship, play with that value, to see how it affects the smoothness and range and all this sort of stuff. Okay, so there you go. There's that LFO and the sort of biasing. I don't know if biasing is the right word for these JFETs, but circuit, basically setting the center voltage. There you go. And then, just the last little bits. We've got some decoupling capacitors for the op amps, just placed on the power rail, and then the LED trim pot to control the brightness of the LED. There you go. Now, here is the board layout. A few things to note. You've got some surface mount ICs. You've got the strip resistor. Here's the 10K one. That's everything's in parallel. It's got one common pin. Everything else is in parallel. I should note that this is 6 pins, which is 1 common pin and 5 resistors, but we're only using 4 of them. So it actually makes it so it doesn't matter which orientation you put that one in. It works either way. And then there's 2 strip resistors here, and then those ones are actually symmetrical, meaning you can flip them. So basically these strip resistors in this particular pedal. You don't even have to pay attention with the orientation. Just stick them in. Here are our matched transistors. Oh, and then we've got this level trim out, which I forgot to mention in the schematic. This sets the output volume, which you may want to adjust just depending on how you set the input volume. If you want a little bit of a boost, where is unity? Are you going to be adding more resonance? That might cause more volume, so you can kind of make adjustments there. Okay, all right, now the connection points here on this. First of all, it's a 4-layer board. So you can see there's the red, the blue, and then there's kind of like the dashed red and dashed blue. 4-layer board because of how many cross connections and stuff with the phasor circuit. We have an input pin is being used. The buffer pin is not being used. Negative voltage and positive voltage are both being used in this circuit. The ground obviously is always being used. We've got the output, the LED, and the foot switch. Those are always being used in all the pedals. Okay, now a couple of things. First of all, if you wanted to take the time to sit down with the Eagle file on this and figure out how to take basically this as is and make it, route it so that it's only 2 layers, I'd love to talk to you about that. Be willing to give you some not money, because I'm not going to have that kind of free cash flow, but value as far as parts or DIY files, those kind of things. That just holds true for all of the 4-layer boards out there. If you're able to, if you think you're able to figure it out, we can just come let me know. Now that said, there are going to be some like sort of particulars that I have, so don't just get started and then be like, I solved it, and then have me go, that's not going to work. So just that one thing. And then what was the next thing? Oh, and the next thing is that I found that combining the tractor beam with the SPS system, the charge pump on that, for whatever reason, the interaction with the LFO was causing a faint but audible click when it would, so you speed it up, you get more clicks. It's super faint, so if you're using it clean, it's like you can hardly even hear it. But if you put a distortion or a gain pedal after this phaser, it becomes pretty obvious pretty fast. Or if you're just playing at super loud volumes, then obviously you'll hear it. So I didn't have that same. There's always a click in an LFO. I mean, that's just true. It's power changing, but it's quite minimal in the previous versions. So if you use the true soft bypass version, which you'd have to hand assemble, that one should work just great. Okay. All right. There's the in-depth explanation. Please let me know if I just got something wrong. That I'm always trying to learn. And let me know if you've got any questions. Thanks.